Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. We're covering a conversation from Latent Space featuring Olivia and Mia from OpenAI's Research and Frontier Evals teams. Their findings expose critical flaws in how we measure AI coding performance. Models achieving record scores on industry benchmarks may not be demonstrating superior engineering ability. Instead, they're exploiting memorized patterns from training data. The discussion centers on why current evaluation methods fail and what standards should replace them. The OpenAI Frontier Evals team has documented systematic failures in how the industry evaluates AI coding capability. The assumption underlying progress tracking is straightforward. When a model's benchmark score increases from 80% to 92%, the model has become more capable at software engineering. The team's analysis contradicts this. They found that SWE-Bench Verified, the most widely cited coding benchmark, no longer measures problem-solving ability. It measures pattern recognition and memorization. The core issue is data contamination. Models are not deriving solutions from problem specifications. They are retrieving answers they encountered during training. The team examined internal reasoning traces from a model designated GPT-5-2. In one case, the model's chain of thought revealed it was referencing a version of a code repository that did not exist at the time the problem was set. The model explicitly reasoned about a future implementation detail, a specific function argument introduced in a later update, and incorporated it into its solution. This constitutes a breakdown in test validity. The model was not solving the problem as presented. It was recalling a known future state from its training corpus. What appears to be logical reasoning is actually high-fidelity reproduction of memorized data. The benchmark is no longer assessing coding skill. It is assessing how effectively a model can surface training examples without explicit retrieval. Small score improvements that companies highlight as breakthroughs are artifacts of this contamination. A 0.1% gain on the leaderboard does not reflect enhanced reasoning. It reflects marginal improvements in guessing exact naming conventions or implementation details the model has seen before. The metric has decoupled from the capability it was designed to measure. Beyond benchmark contamination, the team challenges the definition of acceptable code. Industry evaluation is centered on functional correctness. If the code passes unit tests, it succeeds. The team's position is that passing tests is now insufficient. They introduce a second criterion, design taste. A model can produce code that executes correctly and passes every automated check, yet remains unsuitable for production use. The code may be unmaintainable, stylistically inconsistent, or structurally poor. The team draws a distinction between solving a problem and solving it in a way that a human maintainer would accept. Passing a test does not guarantee that an open source project would merge the contribution. The gap between functional correctness and professional acceptability represents the new evaluation frontier. This redefines what it means for an AI to match human performance in coding. The standard is no longer whether the machine produces working code. The standard is whether the machine demonstrates the subjective judgment of an experienced engineer. Qualities like maintainability and stylistic coherence, previously considered secondary to function, now determine whether AI-generated code is economically useful. Addressing these deficiencies required a methodological reversal. The industry has pursued scalable, automated benchmarks because human evaluation is slow and expensive. To repair SWE-Bench, OpenAI deployed the opposite approach. They hired nearly 100 expert software engineers to manually review every problem in the dataset. The team found that over half the problems in the original verified set contained unfair test conditions. Some expected specific function names not mentioned in the problem statement. Others required undocumented features. The only method to identify these flaws was line-by-line human audit. Automated scripts could not detect the subtle inconsistencies that made problems unsolvable without prior knowledge. This creates a paradox in AI development. As models become more capable, verifying their output becomes more labor-intensive. Evaluating an AI that performs at or above junior developer level requires senior developers to manually inspect its work. The cost of validation does not decrease with automation. It increases because the nuance required to assess quality exceeds what any script can capture. The team is shifting evaluation focus from technical metrics to economic impact. They have developed GDP-Evals, which measure model performance against 15 to 16 white-collar professions that constitute significant portions of economic output. The objective is no longer to determine whether a model can write syntactically correct Python. The objective is to determine whether the model can perform the economic function of a professional worker. This changes the relevant question. Instead of asking whether AI passes coding exams, The team is asking whether AI can replace labour in specific industries. Future progress will not be tracked through test scores. It will be tracked through labour displacement rates, cost savings, and productivity gains. The team describes this as the evaluation framework for AGI. The transition is from treating AI as a computer science research problem to treating it as a force that restructures labour markets. The pattern across these findings is consistent. The tools we built to measure progress have been compromised by the systems they were designed to evaluate. Models have not outsmarted tests through superior intelligence. They have exploited the test by memorizing answers. Benchmarks that once provided reliable signals now generate noise. If validating AI performance requires deploying large teams of human experts to manually check every output, the question becomes whether we have automated the work or simply created a more complex oversight problem. If you're interested in the video featured in this episode, click the link below to watch the original.